we're given that the nth derivative at 0 is n plus 2 factorial divided by 2 to the n. And that's true for n greater than or equal to 0. Which of the following is the Taylor series for f of x centered at 0? And we have a whole bunch of sums. Instead of just reading them out, I'll let you look at them. Hopefully you have been looking at them. And so we have 5 potential answers. A, B, C, D, or E. Do we have an answer? Does somebody have, like, I think I got it? What is it? I see a hand up. What? E? Are you sure? Good. Good. E is the correct answer. Yes. So, what's going on? Well, I'll say this again in a few minutes, but it's good to say it now. Taylor series, you can think of it as though they're storing the derivatives. So, to have the derivatives is equivalent to having the Taylor series. They go back and forth. And in particular, there's just the generic expression. If we're centered at 0, then our Taylor series looks like the sum from 0 to infinity, the nth derivative at 0, divided by n factorial x to the n. Now, that x to the n is secretly x minus 0 to the n, but we usually don't write that out. So we know what the nth derivative at 0 is, because they told us. So we put that in. It's n plus 2 factorial over 2 to the n over n factorial. The 2 to the n goes downstairs. And then we say, oh, n plus 2 factorial over n factorial. That feels like things we've done before. That was one of those things where we had like that ratio test kind of idea. And we could pull terms off of one of the factorials until we could get to the point of cancellation. And so in particular, n plus 2 factorial over n factorial turns out to be n plus 2 times n plus 1. And that gives us the form, and that matches with E. All right, good. Well, any questions on that problem? All right, well, in that case, we'll go to our thought for the day. So, champions do not become champions when they win the event, but in the hours, weeks, months, and years they spend preparing for it. The victorious performance itself is merely the demonstration of their championship character. And I think this is true for any major success, right? You doing well on the exam is not some strange one-time occurrence, but it's accumulation of all the time and effort that you've put into learning. All that time working on problems, thinking about ideas. Why does this work? Why does this not work? So don't look for one-time strokes of genius to hit you and pray for miracles. Prayer is fine if it helps, but put in the time. Put in the time. And all right. Now, what's our goals for today? Well, not too much. We're going to do some more practice with Taylor series, and we're going to introduce one more series, the binomial series. And you may have remembered something like binomial theorem from algebra, where he said, oh, if I expand x plus y squared, I get x squared plus 2xy plus y squared. Or x plus y cubed is x cubed plus 3x squared y plus 3xy squared plus y cubed. And he had these things called binomial coefficients. And the punchline is, yep, and that still works even when our exponent is not a nice number. So nice numbers are like 2 and 3 whole numbers. But we are going to do it with any exponent. So alpha is arbitrary. Could be a fraction, could be a negative number. Doesn't even have to be rational. It could be anything. And so the punchline is it's the sum of the binomial coefficient alpha choose n, z to the n. And this holds for z less than 1. Now what is the binomial coefficient? Well, that's alpha choose n. Looks like alpha minus 1, down to alpha minus n minus 1. And downstairs n minus 1, n times n minus n minus 1. Now, normally, people just write this as n factorial, but here's sort of the punchline. The reason I like to write it this way is when you look upstairs, you have n terms multiplying upstairs, and when you look downstairs, you say, well, how do I make an n factorial? You have n terms multiplying. And they both behave in essentially the same way. You just say, okay, start at the alpha upstairs, then subtract 1, then subtract 2, and keep going till you've got n terms. Start at the n downstairs, then subtract 1, subtract 2, until you have n terms. And once you understand that, it's like, oh, that's not so bad. That's a lot easier than people may make it seem. And I will point out, this is on the formula sheet, right below the other Taylor series. And with that formula, we now have finished the formula sheet. So we now have come to the end. No new equations after that. Everything's something we already knew coming into class or we've talked about. All right, so that's where we're going. Let's start moving. And we'll start where we stopped last time. So we have some basic Taylor series. These are just in our pocket, ready to pull out when we need them. So 1 over 1 minus something, we didn't call it a Taylor series when we introduced it. We called it the geometric series, but it is a Taylor series. There's a nice philosophy that says, if you have found a series for your function, it's the Taylor series. And it's not a very deep thought. It basically boils down to the idea of like, if two polynomials are equal, then their coefficients always are equal. That's what it means. To say when we found a series, we found the series. We then found e to the something, cosine something, and sine something. And these are all very similar to each other. And in fact, we'll just mention something in a second that helps tie all those together. Now, besides the binomial series, which we'll talk about today, that's pretty much the end of us finding Taylor series by actually going through and taking derivatives. Because it turns out for most functions, it's hard to take high-order derivatives and find a nice pattern. But nevertheless, we'll be asked questions such as, well, hey, can you find the Taylor series for this particular function? And you might say, well, how can we do that? Well, my advice is to say, look, don't start from scratch every time. Don't reinvent the wheel. Most of the functions that we're going to have to find the Taylor series for whatever reason, are similar to functions we already know the Taylor series for. All we have to do is adapt them. So we can take them and say, all right, let's modify them appropriately. Maybe we'll change what's on the inside, so what's in the box. Maybe we'll integrate or differentiate. That gets into some of our applications, which we'll talk about next week. Or maybe we'll do some ways of combining things, adding or multiplying. But that's our goal. Now, I feel like I can't feel right letting you finish Calc 2 without pointing something out, which is to say, gosh, E looks a lot like cosine and sine in some respect. And so you may already know this. If not, don't stress too much about writing this all down, but I'm just going to point this out. There's this number we call I. Some people call it the imaginary root. I squared is -1. And, well, it turns out because I squared equals -1, if you keep multiplying I by itself, it falls into a pattern. So I squared is -1, I cubed is I to the fourth is back to 1, and it just repeats every 4 steps. 1, I, -1, I, 1, I, so forth and so on. Now, plug I times x into the exponential function. Because we said, look, that's true for anything. You might be suspicious. It's like, Steve, that seems true for anything, but shouldn't we be keeping it real in our class? Well, okay, all right. I know this is getting a little bit complex, but let's just go with it for a moment. So if you plug in I times x, and you say, well, what does that turn out to be? You have I to the k, x to the k over k factorial. And then your powers of I follow this nice pattern. And so if you write down what happens with your powers of I, you get this expression. And you'll notice I'm grouping things. I've underlined the real parts in green. In other words, things without I. So the 1 minus x squared over 2 factorial, x fourth over 4 factorial, minus x 6 over 6 factorial, and so forth. Those are the real parts. So I put those all together. And then the parts with I, which we often call the imaginary parts, ix minus I x cubed over 3 factorial, I x to the 5th over 5 factorial. Well, I'll put all of those together. And they all have I, so I can pull it out. And now we say, hey, those series look familiar. So, what do we see? Well, for the real part, we see cosine x. And for the imaginary part, we see sine x. That's the Taylor series. So we get e to the ix is cosine x plus I sine x. Now this leads to all sorts of fun facts. So for instance, one of the very famous equations, what is e to the I pi plus 1? Does anybody know this one? It's 0. This is, some people say, this is just such a great equation because it involves so many cool math things. Now, why is it true? Well, plug in pi. Cosine of pi is minus 1, sine of pi is 0. And so you end up with e to the I pi is minus 1 plus 1 is 0. Now, you can also do things such as double angle identities. Okay, so let's just point this out. A fun little exercise. Cosine 2x plus I sine 2x. According to this, that's where we've put in 2x's. So that's e to the I to the 2x. Yes? It's true. I haven't lied. Now we can use properties of exponents to say, well, you know, this is e to the ix squared. Yes? Well, what's e to the ix? That's cosine x plus I sine x squared. Okay, so we just have to square it. So let's square it. So you have a squared, which is cosine squared. And then I'm going to put the b squared right next to it. What's b squared going to be? Minus sine squared. Okay, so that's a squared plus b squared, and then plus 2ab. So there's an I, then 2ab. And now, what do we see? The real part, cosine 2x, has to match the real part. So cosine 2x is cosine squared x minus sine squared x. So we just proved the double angle identity for cosine. Similar, the imaginary part, sine 2x, matches the imaginary part for that. So sine 2x is 2 sine x cosine x. So again, double angle identity. And almost all trig identities that we use can actually be derived in a similar way. So there's lots of fun stuff. All right. So, good. I've done my civic duty. Now, back to our regularly scheduled program. We want to take our basic Taylor series and adopt them. That's our mindset. So, find the Taylor series for the function x cubed e to the minus 2x squared centered at x equals 0. And then it says, while you're at it, can you tell me what the 21st derivative is at 0? Okay. So, let's think about the second part. What's one way we could do part B here? Because there's really two parts. Find the Taylor series, find the 21st derivative. Do we have to have the Taylor series to find the 21st derivative at 0? No, you don't. But what would you have to do? You'd have to take 21 derivatives. We would fill up the whole page by the time we got to the 4th or 5th derivative, and we'd only just started. So probably it's hopeless to actually find the 21st derivative at 0 by finding the 21st derivative. And yet, nevertheless, we will find the answer. Okay, so let's start with the first part, though. We have to find the Taylor series. Now, Taylor series, think of them as polynomials. So as we look at this, we have two pieces. The x cubed, the e to the minus 2x squared. As of right now, which part are we happy with? If we're thinking of our polynomial mindset. The x cubed. X cubed is already polynomial, like, oh yeah, polynomial. So we're happy with the x cubed. We like the x cubed. So it's saying we really need to focus on this e to the minus 2x squared. So let's talk about that. Now we look in our notes and we say, well, e to the something is the sum, 0 to infinity, of something to the k over k factorial. Now, in the actual formula sheet, it doesn't say a box. It uses a letter. I wish it had used a box. But that's what we have for the exponential function. So, with that in mind, what can we do? What is e to the minus 2x squared? Well, we just ask ourselves the question, what's in the box? So what have we put into our box? Minus 2x squared. So we say, okay, so we're putting in minus 2x squared. So we just put minus 2x squared in everywhere. So we're going to have minus 2x squared to the kth power over k factorial. We can adapt. We don't have to take derivatives. We say, look, we've already did the hard work for the exponential function. So if we can modify it, let's do that. Let's be nice to ourselves. We like ourselves. We want ourselves to succeed. All right, so this is, by the way, the same as the sum, 0 to infinity, minus 2 to the k, x to the 2k, over k factorial. So I'm just distributing the k in. So this says, oh, that other piece, that wasn't polynomial, that e to the minus 2x squared, I can tell you how to write it as a polynomial. I can use what we know about Taylor series. So, coming back to our function. We said our function f of x was x cubed e to the minus 2x squared. So we said, well, the x cubed, that's good, that's a polynomial. And now the e to the minus 2x squared, we've written as a series. So essentially that's a polynomial. So that's good too now. And what's one more thing we should do? And not boxing, not yet. There's one more thing we should do. I know, it's like, oh, Steve, box it, box it. I know you like to box. Box it! Box it! No, not yet. One more thing. So what? Because right now, what do we have? We have polynomial times polynomial. But we'd like to have one polynomial. What can I do? to put these together? What can we do? What can we do? And now, what? Distribute, meaning, let's put the x cubed in. Ha-ha! Oh, wow! Fancy. Cool. Okay, so if we multiply the x cubed in, we're putting it all together. We get minus 2 to the k, x to the 2k plus 3 over k factorial. Now that is a beautiful answer, and that deserves a box. Okay, so that's the Taylor series. So the Taylor series for the function x cubed e to the minus 2x squared is this expression. And notice that no derivatives were harmed in the making of this Taylor series, because we just used what we already knew. Now, any questions on this part? Use what you know. And if there's no questions on that part, now we go to part B. Find the 21st derivative at 0. Okay, so before we talk about that, let me just sort of tell you the mindset you should have. If you channel your inner Calc 1 student, Calc 1, we were so innocent back then. But one of the things that we would talk about said, hey, if I have a tangent line at x equals a, so if I had this, what I really had was I had f at a and f prime at a. So somehow the tangent line stored information about the value of the function, the value of the derivative. So if I had a tangent line, I had these two pieces of information. If I had these two pieces of information, I had a tangent line. That was Calc 1. Now we're here at Calc 2. And we say, well, now we're not doing a tangent line. We're going to do a Taylor series at x equals a. What do we have now? So the tangent line had two pieces of information. What does the Taylor series have? Has f of a, has f prime of a, has in fact all the derivatives. So all the derivatives are being stored in a Taylor series. So the Taylor series says, if you have my Taylor series, you have all my derivatives. If you have all my derivatives, you have the Taylor series. That's what we did in our warm-up problem. So there's this back and forth action. Now, even if you got the Taylor series by not taking derivatives, you still have them. They're still there. And in particular, what does it come from? Well, there's this nice formula that says, hey, f of x is the sum, n equals 0 to infinity, the nth derivative at a over n factorial, x minus a to the n. Okay, so that's where we're storing it from. Now, back to our question. We're after the 21st derivative at 0. Can we find it? And how do we find it? Well, if I want the 21st derivative, remember, it's the coefficients that are storing the derivatives. If I'm after the 21st derivative, what coefficient am I looking for? So the constant stores the function. The coefficient of x stores the derivative. The coefficient of x squared stores second derivative. The coefficient of x cubed, third derivative. What derivative are we after? 21st. So what coefficient are we looking for? 21st. Okay, so idea, and here's our idea. Let's look at the coefficient of x to the 21st power. Now, if I'm using just the generic, let's make a Taylor series, and here we're specifically at 0, so a equals 0. According to just the generic definition, what do I have if I look at the coefficient of x to the 21st power? What do I have if I'm looking at the x to the 21st? What's the coefficient? It'll be the 21st derivative evaluated at 0, divide by 21 factorial. So that's if I just look at the definition of a Taylor series and say, what's my coefficient of x to 21? Now, we come here and say, I want x to the 21. Now, let's be careful here. Does that mean k equals 21? And why not? If k equals 21, what power of x do you have? 45, right? Because it's x to the 2k plus 3. I want the 21st power of x. So, which value of k do I want? Sorry, what? 9, right? Good. So, here, if we choose k equals 9, then what we have is if we go a couple pieces out, then we'll have minus 2 to the 9th, x to the 21 over 9 factorial, and then we keep going, dot, 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 right? So k equals 9, that gets me the right power. So what's the coefficient? It's minus 2 to the 9th over 9 factorial. What did we want? We wanted the 21st derivative. So we said, okay, so then the 21st derivative at 0, we just move that 21 factorial across, minus 2 to the 9th power times 21 factorial divided by 9 factorial. And we're done. So if you're after a specific derivative, you say, great, let me figure out what my Taylor series is. And then I say, what coefficients do I have to look at? Compare the two and grab what you need. Any questions on this? See a hand up?
Where did the x to the 21st go?
Well, because we're looking at the coefficient of x to the 21st. So I don't need to include the x to the 21st. I'm just saying what's in front of the x to the 21st. So it's not so much that the x to the 21st, where did it go? It's just that I'm looking at what's in front of them. That's what happened. All right, good. Well, I will assume that you'll do great on this type of question, should it ever happen again. All right. Binomial series. So our goal, our last Taylor series, what's the Taylor series for 1 plus x to the alpha? And now it's just a very simple observation. It says, oh, this is a really easy thing to take derivatives of. It's basically like x to the alpha. Because the derivative of the inside, derivative of 1 plus x is 1. So every time I take a derivative, the power comes down and I subtract 1 from the exponent. So if I start with 1 plus x to the alpha, the first derivative will be alpha, 1 plus x to the alpha minus 1. And then the next derivative, the alpha minus 1 comes down. So it's alpha times alpha minus 1, 1 plus x to the alpha minus 2. And I can keep going. So the nth derivative has a very simple expression. You take alpha, alpha minus 1, all the way up to alpha minus n minus 1. Now that's a total of n terms in front, and these are numbers, there's no x's involved, times 1 plus x to the power alpha minus n. And now if you plug in 0, Well, 1 plus 0 is 1, and 1 to a number is 1. So our conclusion is the nth derivative looks like alpha times alpha minus 1 times all the way up to alpha minus n minus 1. Well, we know how to form a Taylor series. We did it earlier today. Take the nth derivative at 0, divide it by n factorial, and that's it. And then for convenience, we're going to take this expression where we take the power of alpha minus 1 all the way to alpha minus n minus 1, divided by n factorial. We call that the binomial coefficient. So we end up with alpha, choose n, x to the n. Now we're going to skip the details, but if you carry out a ratio test, and this feels ratio test-like, because essentially you get things that look like factorials. It holds as long as x is less than 1. And again, the binomial coefficient, we mentioned this before, it's n terms multiplying on top, n terms multiplying on the bottom. The only difference is your starts. Upstairs, you start at alpha, and then you keep going down by 1 until you get n terms out. Downstairs, you start with n, and then you keep going down by 1 until you have n terms out. And that's the derivation. Any questions on that one? Let's try this out. So, find the Taylor series for the function 1 over square root of 1 plus x centered at x equals 0. So, what's another way to write 1 over square root 1 plus x? Say I was saying I want to make it more calculus friendly. Sorry, what? No. I'm just saying rewrite 1 over square root 1 plus x. What's another way to write that? 1 plus x to the negative 1/2. Negative because it's downstairs, and 1/2 because, well, it's a square root. Now, why do we like to write it this way? Well, because we come back here and say, hey, we have an expression for 1 plus x to the power. 1 plus x to the alpha is this expression. So, now we just say, according to our rule, we have 1 plus x to the alpha, so this is the sum, 0 to infinity, alpha, choose n, x to the n. Well, that was really quick. We have all this space. So let's do something, since we have all this space. Let's ask another question. What's negative 1/2? Choose n. Let's see if we can't figure that out. So I want to actually rewrite that. So we're going to put a box here in anticipation. I want to say, can we figure out what negative 1/2 choose n is? Now maybe we can do some simple warm-ups. Negative 1/2 choose 0. By convention, any thoughts on what this should be? What? 1. Good. Now you might say, wait, how does that work? Well, if you come back to here, when I'm having negative 1, alpha choose n, it says you have n terms upstairs, n terms downstairs, multiplying. So I have no terms upstairs multiplying, and I have no terms downstairs multiplying. When you have nothing and you multiply nothing, what do you get? 1. Now that sounds strange, but I didn't say you had 0 and you multiplied 0. You had nothing and you multiplied it. All right. Negative 1/2 choose 1. What does that look like? Well, upstairs, you start with negative 1/2. Downstairs, you start with 1. And how far do we have to go? Well, we have to get one term on top and one term on the bottom, so we're done. So it's negative 1/2. How about negative a half, choose 2? So start upstairs with negative a half. Downstairs you start with 2, but we need 2 terms. So it's 2 times 1. What do you have upstairs? Negative 1/2 times. What comes after negative a half? Negative half minus 1, also known as negative 3/2. If you multiply this all together, we get 3/8. Minus a half, choose 3. Upstairs, we're going to start with minus a half. Downstairs, we're going to start with 3. And the downstairs is easy, 3, 2, 1. We just go down. Upstairs, what comes after negative a half? Negative 3/2. It's the same thing as we had here. Then what's the next term? Negative 5/2. And if we multiply that all together, what do we end up with? (5/16), I think. Because you can cancel a 3. And there's a negative, because there's 3 minuses. And 2 times 2 times 2 times 2. All right, so we have 1 minus a half, 3/8 minus 5/16. Okay, that's something. Let's do it in general. Minus a half, choose n. So we'll have downstairs n minus 1 all the way down to 1. Upstairs, we'll have minus 1/2, minus 3/2, minus 5/2, and we're going to keep going all the way to minus a half, minus, and minus 1. All right? That's the rule. Okay. Well, one thing we can do is we can factor a negative out of each of the terms upstairs. How many terms are there upstairs? N terms. So there's if I factor out a negative, that's negative 1 to the n. And I can factor out some 2's. How many 2's are there? There's n. So I'm going to factor out negative 1 to the n, 2 to the n. Then I have 1 times 3 times 5 times all the way up to this last term. So let's be careful with this last term. We factored out negative a half, so that's going to come 1 plus 2 times n minus 1, which is the same as 2n minus 1. So that's the last term. So it's an odd number. Then downstairs we have n times n minus 1 all the way to 1. All right, so that's where we're at. So downstairs was an n factorial, but the upstairs, what does it kind of feel like? 1 times 3 times 5 all the way up to 2n minus 1. What does it feel like? With feeling, what is it? It's like, oh, this feels like, oh. Maybe don't start at the beginning, start at the end. 2n minus 1 times 2n minus 3 times 2n minus 5, all the way down to 1. What does it feel like? What is it like? Oh, this really wishes it could be a factorial. It's almost like a factorial. It's like, oh, if only, if only. What's missing for it to be a factorial? The even terms, right? So let's be nice to it. Let's make it a factorial, because we are generous, kind people, right? So we're going to have the numbers we started with, and then we're going to add in some new numbers. So we're going to add all the evens in, all the way up to 2n. Okay? So we're nice. We've added in the evens. But if I add the evens upstairs, what do I need to do? I need to add the evens downstairs. So I still have this n factorial from before. And then I have 2 times 4 times 6 all the way to 2n. Okay, so some good news. Now, we do have a factorial upstairs. So we're happy. The bad news. We now have the other problem. Oh, we have 2 times 4 times 6 all the way up to 2n. That really wants to be a factorial. And I know what you're thinking. Well, let's just add the odds. But no, that would get us back to where we started. So we can't just add the odds. The odds are against us. But what can we do? What do all these numbers have in common? There's nothing odd about them. What do all these numbers have in common? They're even. So if they're even, what can we do? Let's pull out powers. Let's pull a 2 out of each term. We have n terms, right? So if I have n terms, I pull a 2 out of each one. 1 times 2 times 3, all the way up to n. But what's another way to say 1 times 2 times 3 all the way up to n? That's n factorial. Okay, so we've done a lot here, so let's recover. We still have that negative 1 to the n over 2 to the n out in front. Upstairs, we said, hey, by adding the evens, you have a 2n factorial. Downstairs, we had an n factorial, and now we have another n factorial. So that makes n factorial squared, but we also have a 2 to the n. So, last thing is we have 2 to the n's. So we can make this negative 1 to the n. 2 to the n times 2 to the n is 4 to the n. Then we have 2n factorial over n factorial squared. So, what goes in the box? We figured out how to rewrite minus a half choose n. So this becomes the sum, n equals 0 to infinity, minus 1 to the n over 4 to the n, 2n factorial over n factorial squared, x to the n. All right, now that we've had that warm up, we'll do one more thing for today. Any questions? Find the Taylor series for arcsine of x. And I know it's like, of course, I've always wanted that. Now, you're probably like, why aren't you covering this up, Steve? Well, because I don't want to work hard. Our goal in math is to not work hard. At least not too often. Sometimes we have to put in the work. Does anybody remember the derivative of arcsine of x? 1 over square root 1 minus x squared. Now, that looks a lot like 1 over square root of 1 plus negative x squared. Yes? And you're probably thinking, okay, Steve, cool. But why would I write it that way? We have the Taylor series for 1 over the square root of 1 plus something. What can we do? We can replace x by negative x squared. It's our classic what's in the box. So this is the sum. Using the work we already did, I can just copy minus 1 to the n over 4 to the n, 2n factorial over n factorial squared, and then instead of x, put in minus x squared to the n. So use what we did. Now, minus 1 to the n, minus 1 to the n cancel out. So we have the sum, 0 to infinity, of 2n factorial over 4 to the n, n factorial squared, x to 2n. Is this our answer? And why not? It's the derivative. We found the derivative of our answer. So if we have the derivative of our answer, how do we get our answer? You integrate. So we integrate this. Now there's a plus c. I'll go ahead and tell you that the constant will be 0. So term by term integration gives us 0 to infinity, 2n factorial, 4 to the n, n factorial squared, times 2n plus 1 downstairs, x to the power of 2n plus 1. And there is the Taylor series for arcsine.